Do now!
All right.
Here we go.
That's 5, 4, 3, 2, 1.
In the video you just saw, there was a large mylar balloon, and the hydrogen and oxygen gas were mixed inside the balloon. In my little depiction here, this is just a normal hydrogen balloon with oxygen from the atmosphere, and this would, because the oxygen and hydrogen aren't thoroughly mixed together, this is mostly just going to produce a flash and a little bit of a burn. Kind of exciting, but nothing like the hydrogen-oxygen balloon that you witnessed in the video that preceded this slide. So, in any case, here's the chemical reaction that you observed. You had hydrogen and oxygen inside the balloon. A spark was provided, which was the activation energy to stir things up, to get enough kinetic energy going to initiate a chemical reaction which released a lot of energy, which got other molecules of oxygen and hydrogen going. And so then it became this cataclysm of reactions starting from one little tiny part of the reaction. It happened so fast, it just is a big bang. Now, there are two products of that hydrogen-oxygen gas reaction. The chemical product is actually water. That's how you make water from hydrogen and oxygen. And you could probably tell that a tremendous amount of energy was released in this reaction. That's because water is such incredibly stable stuff. Its potential energy is so much lower than the individual oxygen and hydrogen molecules that that energy is released into the surroundings. This is actually, if you take liquid hydrogen and liquid oxygen, that was the reaction that actually powered the space shuttle engines that were actually on the space shuttle itself. The big solid rocket boosters, that was a different redox reaction, but the big tank on the space shuttle was powered by hydrogen and oxygen making water and releasing a lot of energy, and you probably noticed a lot of light as well. Now, thermodynamics is the study of energy relationships, and energy relationships in chemistry is incorporated into thermodynamics. We're going to look at the study of energy and its transformations from chemical energy into heat energy. We'll take a brief look at work as a function, but we're going to mostly focus on the transfer of heat in a process known as enthalpy, or changes in enthalpy in those chemical reactions. But we'll take a general look in this chapter at the study of energy and its transformations from one form to another. And the first thing we need to take a look at is the first law of thermodynamics, which simply says that energy can neither be created nor destroyed in a chemical reaction. Now, that is really a very large idea. And if we sort of broaden that to look at the notion that energy can neither be created nor destroyed in the universe, that says that the total energy content of the universe is constant. So at the beginning of the universe, there was a given amount of energy, but that energy gets transformed from one form into another. However, it's neither created nor destroyed. So what's happening as the universe expands is that energy is simply spreading out in a process which we call the increase in the entropy, or the disorder of that energy. And that is an ever going on, that is an ongoing project that the universe is engaged in, is spreading out that energy. But the energy is neither created nor destroyed, which is incorporated into the first law of thermodynamics. The second law of thermodynamics, which says for any spontaneous process that that energy continues to spread out, which we will not take a look at in this course, but we will study in the second semester of general chemistry. So basic definitions: the system is just the portion of the universe that we select for study. For us, that's just going to be the chemical reaction itself, and we will study essentially the changes in the temperature of the system during the course of a chemical reaction. Does it get colder? Does it get hotter? And what is happening with respect to the energy? Is energy coming into the system from the rest of the universe, which we call the surroundings? And the surroundings are usually the immediate surroundings, but really, if you think about it, if we're studying the system, which is that portion of the universe that we're studying, the surroundings is just the rest of the universe, or everything else. Now, one of the rules that we have is that the system cannot exchange matter with the surroundings. It can exchange energy with the surroundings. And we're going to focus on simply changes in temperature, or the movement of heat either into or out of the system from the surroundings or to the surroundings. So system and surroundings comprise the entire universe. Energy, we need a definition, is simply the capacity to do work or transfer heat. We will focus principally on the transfer of heat. We'll speak a little bit about the work function, but mostly focus for our purposes on the transfer of heat from the system to the surroundings, or from the surroundings to the system. Let's talk about kinetic energy, which is simply the energy of motion, which is encoded into this equation: 1/2 times mass in kilograms, the SI unit for mass, times the velocity squared, velocity being in meters per second. And potential energy is simply stored energy. It's the energy by virtue of location, if we're talking in physics terms, but for our purposes, it will be the energy stored, potential energy, in chemical bonds. And what you'll find out is that bonds, which are the binding energy between different substances, require energy to be broken, and then when bonds formed, energy is released, and it'll be released in the form of heat. So breaking bonds, just like breaking a stick, requires energy, and when bonds formed, energy is released. And so let's take a look at one chemical reaction which is very energetic.
In this experiment, we are looking at the explosive decomposition of a compound of nitrogen triiodide. This brown compound is so sensitive when dry that just touching it with a feather causes an explosive decomposition. It forms nitrogen and iodine. Like this mousetrap, which releases potential energy from the spring, the nitrogen triiodide releases chemical energy. When it decomposes into its elements, nitrogen and iodine.